Okay, recall that I is the vector 1, 0, 0, and j is the vector 0, 1, 0, and k is the vector 0, 0, 1. At least that's the 3D version. If you're in 2D space, of course, there's going to be no k vector, and there are I and j vectors that don't have third components, so just 1, 0 in angle brackets and 0, 1 in angle brackets. Of course, context will always make clear whether you're dealing with a two-dimensional problem or a three-dimensional problem. So these things don't end up ever getting confused. So let's look at the vector v defined to be 3i plus 0j plus 4k. Notice everywhere that there are arrows, those arrows need to be there. And if we replace the ijk with the way they're defined, then we can do our scalar multiplications, right? So I multiply that 3 in, 3 times 1, 3 times 0, 3 times 0, and so on and so forth. Let's see, then let's do our vector addition, right? So we should add component-wise, and we should get 304 in angle brackets. So ultimately what happens is the vector 3i plus 0j plus 4k with the appropriate arrows is the same as 3 comma 0 comma 4 in angle brackets. These are really what end up being two different ways to write the same vector. That is, in the ijk format, if you end up collecting like terms, the coefficients you see in front of ij and k end up becoming the components in that angle bracket format. So following the pattern, you could go through this whole process again, but to summarize it real quick, I think you'll see that 5i plus 1j minus 8k is the same as 5 comma 1 comma negative 8 in angle brackets. Okay, let's take a look at the vector w defined as 3i plus 4k. Now, at first, when it's written in that kind of form of a number times one of those standard unit vectors and so on, it's hard to tell whether you're in 2D or 3D. However, here, I'm giving away that it's got to be 3D because there's that k vector, right? So I'd like to find w dot w. So the remark here is you can dot a vector with itself. As you can see, this question is about a vector dot itself. The dot product is defined for any two vectors that are of the same dimension, right? So you take two three-dimensional vectors and you can dot them, including a vector in itself. So written in the other format, by the way, so I just included the 0j. I mean, there's no j term, but I just included a 0j. Ha, j term. I just thought about that. That's kind of funny for winter session classes. Okay, anyway, I wrote this out as 3i plus 0j plus 4k so that where the 0 as the middle number between the commas appears is a little clearer. And then we can apply the dot product formula, right? So 3 times 3 plus 0 times 0 plus 4 times 4, you end up getting 25 for that. By the way, if we just do a little follow-up, starting with this vector w, which had components 3, comma 0, comma 4, if you ran it through the magnitude formula, you'd get the number 5. And take a look. 25 was our answer for the vector dot itself, and 5 is our answer for the magnitude. And this relationship occurs always. So you'll notice here that the magnitude squared, 5 squared, ends up being the value that we got for the dot product of the vector in itself, 25 in our example. This happens in general. In fact, it's a theorem. This is just one example, but you can do another example and another example, and then you'll really be convinced that no matter what vector you have, the square of the magnitude of that vector is the same as that vector dot product itself. If you want, there is a little proof that I did on this slide. Even if you haven't taken a class on proofs, I think this one's actually fairly okay to follow along on. So let's go ahead and prove this. So if A is any vector, okay, so for any vector, for all vectors, we're going to have to just, pick a vector arbitrarily. The reader of the proof picks a vector of their choice. And either you have a 2D vector or a 3D vector. We'll just do the two cases. And they're not, they're technically different, but morally they're the same. So suppose first that A is a 2D vector. That means that that vector is written in angle bracket notation as x comma y for some reals, right? There exists real numbers x and y such that the vector A is equal to angle bracket x comma y close angle bracket. So then when you do A dot A, you just write out what the dot product formula should give you. You're going to get x squared plus y squared. And if you look at the magnitude squared, well, you run the magnitude, which is going to be root x squared plus y squared, but then that, just surrounding in parentheses still here is squared, and so the square is going to undo the square root, and you're left with x squared plus y squared. So if you take a look, both the magnitude of A squared and vector A dot vector A both simplified to the real number, to the scalar x squared plus y squared. So that works in that case. In case 2, you have a 3D vector called A, and it runs pretty much all the same. It's just there exists scalars x, y, and z such that the vector A equals x comma y comma z in angle brackets, and when you do a dot a, you get x squared plus y squared plus z squared, and when you do the magnitude of a quantity squared, you also get x squared plus y squared plus z squared. So in both cases, the magnitude of the vector then squared simplified to the same real number as the vector dot itself. That's the proof.